my name is Ruben Wiersma and I'm here to talk to you about ALPS. Well, not these ALPS, but ALPS, Abstracted Low-Poly Stylization and Fabrication. In our paper, we try to stylize images into the low-poly style. These images use only polygons, often triangles, at low counts, and their faces are then colored with flat shading. Outside of digital art, this is widely used in fabrication. For example, simple facets with limited materials are used in stained glass, woodworking, Tiffany-style glasswork, and embroidery. So our task is as follows. We're given an input image and/or a text prompt, and then we want to output a low-poly vector graphic. Now, in both the digital and the fabrication setting, we find the following properties to be important. First, we want control of the triangulation count and quality. The count determines the level of extraction, and the quality can have effect both on the aesthetics and the fabricability. For example, small triangles with sharp angles will easily chip off and damage when fabricated. The second property is that we want control of the color palette, for example, to have certain styles, and we want to be able to quantize this color palette to a fixed set of colors. This is essential for fabrication, for example, when only a fixed set of glass colors is used. And finally, we want the triangles to form a manifold tiling. That basically means that we don't want any intersections because it both looks bad and, of course, it's hard to fabricate. Now, this low-poly style has been covered in prior research. Early on in 1998, Garland and Hegbert already simplified an initial 2D triangle mesh using a formulation of the original quadratic arrow metric that accounts for appearance attributes. More recently, Lavon and Günther and Triangula use optimization-based methods to place vertices and assign colors per face to match the appearance of an image. A downside of these approaches is that they are all appearance-based and they do not incorporate semantics or aesthetic quality or approximate the low-poly styles it has evolved over the years. In our approach, we use semantic priors, and the low-poly style features are captured through a diffusion model. Image generation models capture the low-poly style really well, but they output raster images, and they contain many non-triangular and non-polygonal elements. A good takeaway here, though, is that we do expect that a diffusion model can capture this low-poly style concept in its weights. There are also generative methods that can output vector graphics directly, but these often contain many issues like overlapping and intersecting triangles and no control of the triangle colors or quality. Now, we like explicit representations like vector graphics, but if the representation doesn't hold up to certain quality standards, you might as well start completely over. Therefore, we argue that it's important to have strict control on the representation, not just the content and the look, but also the representation, and this is where our method comes in. So ALPS optimizes a 2D mesh and face colors to match the semantic context of an image or prompt. We use a diffusion model to guide the optimization for two reasons. First, it captures the semantic content of images well. And second, we observe that in the raster graphic setting, it also captures this low-poly style well. Now, I want to note that we build here on the work done in SwiftSketch, which uses a diffusion model to generate sketches. Now, the remaining challenge is to get an output vector graphic that satisfies the constraints that we set. A first challenge is that we have to represent the colors in a way so that we can optimize the topology. So that means our list of triangles changes during the optimization. Therefore, simply storing a list of color values per face can be fragile. So instead, we encode the colors as a continuous color field, which is sampled at the barycenter of each face. In addition, we want to limit the colors to a color palette. Therefore, the multi-layer perceptron that encodes this continuous color field outputs a set of convex weights for the colors in the palette. In the optimization, we then also add a loss to have a sparse assignment to be as close to the quantized state as possible. We can then choose to use softmax or argmax to assign the final RGB colors. For our optimization, we need three components: an initialization, an optimization loop that can also adjust the mesh topology, and an energy function or loss that encodes our desired properties. For our initialization, we sample points according to a saliency map and then compute a Delaunay triangulation, after which we fit with least squares the colors to the input image. We then optimize vertex positions and face colors through score distillation sampling. We render a raster graphic of our triangle mesh with a differentiable render and add noise to the output. Then we query a diffusion model conditioned on a prompt and a depth map to estimate the noise that was added. Now, the insight behind score distillation sampling is that the estimated noise doesn't just contain noise, but also contains changes to the input image that would push it more toward the expected image given our conditioning. This then updates the colors and the vertex positions, but we can't do the same for the topology because it's discrete. A key insight is that we can use the flat color palette assignment to our advantage to optimize the topology as well. Let's say that we start with a high resolution mesh and start coloring faces. The diffusion model could assign multiple adjacent triangles the same color. In this way, we virtually create a coarser triangulation, but in a differentiable way. This is encouraged in the optimization through two ways. First, of course, through the conditioning of the model in the low-poly style. And second, by the loss that pushes colors to the color palette. During the optimization, we clean up the edges that are not required anymore by finding the coarser mesh that best approximates the current image. You could see this as a projection step in projected gradient descent. And luckily, we can reuse standard mesh simplification methods, here the line quadratic algorithm, because it works well in flat regions. And we can use this to do our projection step. Now finally, our optimization includes terms that encourage high-quality triangles. We also encourage vertices to snap to certain lines, for example, the edges of the artwork, or to mirror symmetry lines, and we add several measures to prevent intersections. More on this in the paper. Let's take a look at some results. ALPS works on a large diversity of inputs. We showcase here many examples where objects, animals, landscapes, or people are depicted. If you can tell what each of these designs are, even with low polygon counts, that means our method properly optimized on semantic features, despite the constraints in resolution and color palette. The color palette can be given as an input to the method, and we showcase here that the variations for the color palettes actually also change how the geometry is used. This is because we jointly optimize both the color assignment and the face topology. The user can also fully control the target triangle count. And even as we lower the resolution, we tend to preserve semantic features best. Now these methods that we compare to here rely purely on geometric approximation and appearance approximation of the input. Now given a color palette that is very far from the input image, ALPS can still operate with very high readability. As the triangle resolution goes down, our method is also better at preserving the semantic features that matter most for keeping the subject of the image. We process an input image with a fixed color palette and provide a valid manifold triangulation. Therefore, we can create designs that respect constraints for fabrication applications. Here you see an example of a skier that has been discretized with 6 colors, and we then fabricate it as a piece of embroidery with 6 pieces of thread. Because we have full control of the representation, we can also incorporate additional geometric constraints. For example, we can fix the vertices on the boundary to a circle, or we can make sure that the topology follows a Eulerian grid. That means that every edge is only traversed once when we trace it with an embroidery machine. There are also other applications. For example, we can use the color palette to map to certain types of wood, and then we can create a beautiful wood mosaic. We laser cut each wood layer and assemble them to give the results that you can see here. A very similar example uses faux stained glass. So here we use colored types of plastic. We laser cut them and we assemble them according to the input image. You can use it for stencil painting, where you can cut sheets that stay together because we have the edges connecting them, and then spray paint over them. And we go back to textile design with patchworking, where we first merge the triangles with the same color, creating polygons instead of just triangles. Then we cut them and sew them together. Finally, we also created 2D crochet designs, where contrary to standard designs that require many color jumps, we use a patch-based approach, where we first create the patches and then sew them together. So to conclude, we presented ALPS, a method that creates a low-poly representation by optimizing a planar triangular graph. Because we use a pre-trained diffusion model, we can incorporate semantically driven gradients to make the results more faithful to the input on a semantic level. A downside is that our approach requires more time than a typical feed-forward method. You can count on about 5 minutes per design. In the future, extending the realm of representable planar graphs to the curved edges or arbitrary shapes is an interesting challenge and would directly transfer it to many of the applications we presented. Thank you for your attention. The fabrications can be found at the IGL lab in Zurich, and you can find the code and more information on the project page or the links here.